In this video, I want to talk about chapter 5. Chapter 5 is all about dot products and what are called inner products. And the dot product is something that if you've taken any course in Calc 3, you've seen the dot product. It's one of the first things that comes up in that course. And so it has to do with vectors, which of course is why we're doing this after chapter 4. So what I want to do is I want to talk about the dot product in vectors in R2 and R3. And then we can generalize this idea of dot product to arbitrary vector spaces, and that's what inner products will be. So let's do that. So what I want to do in order to introduce this idea of a dot product is I want to kind of give you a little bit of geometric intuition. So there's a little bit of geometry and a little bit of trigonometry involved here. But the idea is, say I have two vectors in R2. I can only draw in R2. I can't even pretend to draw an R3. So say I have two vectors in R2, call them U in V. Okay, and so these are vectors. And what I want to do is I want to think about what's the angle between the two vectors. Perfectly reasonably geometrically coherent question, right? We want to know what's the angle between the two vectors. And so in order to kind of study how this is going to work, what I'm going to do is I'm going to think about a few things here. I'm going to notice that this angle theta here is this angle between the two vectors. And I want to think about this angle between V and the x-axis. Okay, so I'm going to call that angle alpha. So alpha is going to be this purple part. And then theta plus alpha is going to be the angle from the vector u to the x-axis. Okay, so if we add those two up, we get theta plus alpha. And it turns out the right thing to look at is we want to know what's cosine of theta. And cosine comes up because we basically we're going to draw some triangles here. So let's think about u as the vector. I'm probably going to draw u and v both with and without the vectors just because the little vector tails here get a little bit annoying to draw, but u and v are vectors. U is going to have components x1 and y1. V is going to have components x2 and y2. And you could think of these as vectors. So, I've written it as a 2x1 matrix. You could write it as a 1x2 matrix, or a, there's lots of ways to represent vectors. So what we're going to do is we're going to draw a few triangles, like I said. And so I'm going to take the vector u, and if I project down, so if I think about just draw a perpendicular line from the tip of the vector u down to the x-axis, I get x1. If I do it over here, I get y1. And then likewise, if I do it over here, we get x2. And I'm not going to draw through my picture, but approximately here is y2. Okay, you can imagine that if I were to have kind of a dotted line, that's y2. Okay, so that's the height of that second vector. And there's no reason really to assume that y2 is less than y1 or x2 is bigger than x1. Just kind of arbitrary choices here work just fine. In fact, there's no reason to even think that the vectors u and v are in the first quadrant. They can be wherever they want. This argument actually is pretty generalizable. And what I want to do is I want to compute cosine of theta, right? I want to know what's the angle between the two vectors u and v. And it turns out that getting the exact angle cosine of theta is really tricky because the vector v here is not on the x-axis. If I were to kind of rotate this, let's see if I can do this. If I were to kind of rotate this so that the vector v was horizontal, then this question would be a lot easier. But it turns out that v in general is not. So we're just going to do this for general vectors. And so the trick here is we're going to write theta as theta plus alpha minus alpha. And then we can use the sum of angles formula from trig. And we know that this is cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. So here I'm thinking about, you can kind of look up if you were to have, right, sine of x plus y or cosine of x plus y. I mean, we know what the sum of angles formula is there. Anyways, so this is what we get. And cosine, we're just thinking about triangles here. So cosine of theta plus alpha, remember theta plus alpha is this angle. Cosine is going to be the adjacent divided by the hypotenuse of the triangle. So that's going to be x1 divided by the length of u. So this is x1 over the length of u. So I'm going to use single bars for the length of the vector u, times cosine of alpha. So that's going to be just a similar thing, but a different triangle. So here we're looking at this triangle. So here the side on the x-axis, the adjacent side is x2, and the hypotenuse is the length of the vector v. And then we'll do the same for sine. With sine, we get the opposite over the hypotenuse. So here we're going to get, let's see, for theta plus alpha, we'll get y1 over the length of u. My iPad just likes to jump around sometimes. And for sine of alpha, we get y2 over the length of v. And so it turns out that what we get is this product, x1, x2, plus y1, y2 over the length of u times the length of v. And the numerator here is exactly what we call the dot product. So this dot product here is this quantity x1, x2 plus y1, y2. So x1, x2 plus y1, y2, we call the dot product of u and v. And so this is the thing that we're going to look at. But already we know a lot. The way that we've defined the dot product was via a geometric picture. And cosine of theta, if it turns out to involve the dot product, well, knowing the dot product and knowing the lengths of the vectors tells us something about theta. So what we can do is we can work backwards. We can be given vectors u and v, and then based on what we just did, based on this calculation, we can go back and figure out what's the angle between those two vectors. And in particular, it turns out that u and v are orthogonal. Orthogonal is a mathematician fancy word for perpendicular. But orthogonal is the real like mature mathematician word that we're going to use. So orthogonal, by the way, means a right angle or a straight angle. Ortho meaning like straight. So you go to the orthodontist or the orthopedist so that they can straighten your teeth or straighten your foot or whatever. So orthogonal just means right angle. Anyways, u and v are orthogonal if, and only if, it turns out, let's think about what this means just for a second. To say that two things are orthogonal means that the angle between them is 90 degrees, right? Or pi over 2 radians. And what's cosine of pi over 2? Well, 0. And so it turns out that u and v are going to be orthogonal vectors. And this is going to hold not just for R2, but also R3, R4, R5, and Rn in general. That two vectors are going to be orthogonal if and only if their dot product is 0. Okay, and so that's going to be the first thing here. We're going to say two vectors are orthogonal if their dot product is 0. And dot products have a lot of nice properties. So in a certain way, what the dot product does is it tells you basically how close u and v are to being orthogonal or pointing in the same direction, if you want to think about it like that. So if you have a dot product that's positive, what that generally means is that u and v are kind of pointing in the same direction, right? Their angle between the two vectors is less than 90 degrees. And if you have a dot product that's negative, that happens when you have a vector u and a vector v pointing in opposite directions, right? Because the angle between the two vectors would be greater than 90 degrees. And so therefore cosine would be negative. And so the dot product can tell you a little bit about the geometry of these two vectors. Okay, so that's the first thing. Just in general, so if we're talking about two vectors, so if I have a vector u and a vector v in Rn, say u is the vector, let's do it this way, x1, x2, all the way up to xn. And v is the vector y1, y2, all the way up to yn. Then u times v, u dotted with v, I should say. So the dot product of u and v. What you do is you take the product of the corresponding entries and then you add them all up. So you got x1 times y1 plus x2 times y2 all the way up to xn times yn. Okay, and so that's what the dot product is. And again, same geometric picture, just my drawing skills are limited. So same idea, the dot product will be 0 if and only if the two vectors are orthogonal. If I want to talk about what orthogonal means in, say, 3 dimensions, it just means that the angle between them. So if you have two vectors, this is hard to show in a video, but if you have two vectors, there's going to be a unique plane through those two vectors, and then you can talk about the angle on that plane between the two vectors. That's the idea. And then geometric intuition is completely gone after 4 or higher dimensions. So if you wanted to get an idea here, if you wanted to talk about an idea of, say, determining whether or not two vectors are orthogonal, all you really have to do is compute the dot product. So if I have, say, the vector 1, 2, 0, and let's say v is the vector -2, 1, 5, then we can compute the dot product u and v to be 1 times -2 plus 2 times 1 plus 0 times 5, which happens to be 0, and therefore u and v are going to be orthogonal vectors. So the angle between them on that plane that containing both of those vectors, the angle between them will be 90 degrees. Okay, so they really are orthogonal. So that's kind of the idea there. The last thing I wanted to say, at least for now, about vectors in dot products is the length of the vector. What do I mean by the length of the vector? Well, in R2, this is pretty easy to talk about. If you have a vector v, you just look at the length of the vector as the length of the x coordinate plus the length of the y coordinate, and then use the Pythagorean theorem. And so it turns out that the length squared is going to be the, so let's say v, just to make this a little bit more precise here, let's say v is, oops, my microphone fell off. So let's say v is the vector v1, v2. Then the length of v is going to be v1 squared plus v2 squared, and then we take a square root because of the Pythagorean theorem. Okay, that's the length of the vector. But notice that this is just the square root of v dotted with v, right, as a dot product, because the dot product of v with itself will be v1 times v1 plus v2 times v2, right? We really do get v1 squared plus v2 squared. And in general, in Rn, so if I have a vector for v in Rn, say I have v is the vector v1, v2, all the way up to vn, it'll be the same story. The length of v is going to be the sum of the squares of its components. So it's all of these values squared and then added up, which is, again, nothing more than the square root of v dotted with v. Okay, so this is an important relationship with the length of v. So the length of v is the square root of that dot product v with itself. Okay, so that's the thing I wanted to say there. Now, the dot product, just a little bit of geometric intuition here and a little bit more geometry. And again, I have to say, you're at an advantage if you've already taken Calc 3. So if you've taken Calc 3, you've seen this story before, but I think a reminder is a good idea anyways. It turns out what we're really doing when we talk about a dot product is we're thinking about projections, so vector projection. So what I mean by a vector projection is, let's say I have a vector u and a vector v. And what I want to do is I want to pretend that I can kind of walk around the vectors, and I'm going to take a flashlight and I'm going to stand here and I'm going to project the flashlight onto that vector u. So this is what's called an orthogonal projection. What I mean by orthogonal is that I'm going to stand on the line that is going to pass through the tip of u and is orthogonal to v. And I want to think about what's the shadow of the vector u that's going to show up on v. And of course, it's going to be this shadow. So if I were to take this vector u, you get this kind of red. Let's make this just a little bigger. got this kind of red vector, which I'm going to call P. P is for projection. And so that P is that shadow that you cast on V. That's the idea. That's what a vector projection is. And I do have to add one more kind of silly case here. When I have a vector U and a vector V, you have to extend V a little bit. You still want to think about what's the shadow of U on the vector V. And sometimes it's longer than V, sometimes it's shorter. Okay, so the fact that it's shorter is not going to matter again. And so what I want to do is I want to come up with a formula for the vector P. And so I want to think about the angle between them, which we already know involves the dot product. And I want to think about what's the vector P going to be. And there's a few different ways to do this, but the way that I really like to do this is to think about kind of, first of all, what's the length of the vector P? And if we know the length of the vector P, then we're done, because if we know the length of the vector P, P is just going to be some kind of dilated vector V, right? You're going to take the vector V, you're going to dilate it, so either shrink it or stretch it. And if you know the factor by what you need to stretch it by, then you're done. Okay, so there's not much more that we need to think about here. We just need to think about what is that quantity going to be. And it turns out that actually the right thing to do is to think about kind of one of the things that'll kind of make this algebra a little nicer is to normalize V. So what I mean by that is you want to make V have length 1. And then once you do that, then everything is fine. So anyways, we'll get to this when we need to. The idea first, though, is if I want to calculate the length of P, I can use what we know about the angle between U and V. We know that if I look at cosine of theta, so if I take cosine of theta here, this is going to be the length of the adjacent side, which is the length of P, which is what we're looking for, divided by the length of the hypotenuse, which in this case is U. Notice, by the way, that the angle between U and P and the angle between U and V are the same because P and V are parallel, right? They're pointing in the same direction. And so if I want to solve this, I know that the length of the vector P is going to be cosine of theta, where theta is the angle between U and V, or the angle between U and P, whatever, times U. Okay, so I get cosine of theta times the length of the vector U. And cosine of theta, we've already talked about how to find, we've already talked about what that is. We know that cosine of theta is nothing more than the dot product of U and V divided by the length of U times the length of V. And then here we're multiplying by the length of U. Okay, and it turns out that the length of U's cancel. Okay, so those U terms cancel. And so the length of the vector P is going to be exactly this. Okay, so it's U dotted with V divided by the length of V. And what this tells you is that therefore P, again, once we know the length of the vector P, we can use that to find K. So just to make this completely clear here, K is going to be, well, the absolute value of K is going to be the length of P divided by the length of V. So here, let me add the tails on the P and V just to emphasize that P and V are vectors, K is a constant, K is a scalar. And so that's what K is going to be, right? So K is going to be that multiplicative constant, right? That stretching dilation factor. And so here, P is going to be the length of P times, let's see, so if we plug everything in here, P is going to be K, which is the length of P divided by the length of V. So this is U dotted with V. I'm just going to assume for now that P and V point in the same direction. And if that's the case, then K is just going to be positive. Okay, because think about, if I take a vector and multiply by 2, that's just going to stretch the vector. It's in the same direction. But if I take a vector and multiply by -2, that's going to take the vector and then flip it and then stretch it by a factor of 2. So here, let's just assume P and V are in the same direction. So K is positive. If K is negative, you do basically the same thing and everything works out. But the point here is that K is going to be the length of P divided by the length of V. And so if you take that and plug it in, you're going to get that P is going to be K, which we just said is this. So that's the length of P divided by the length of V. And the length of P we have a formula for. So once we put everything together, we get the length, we get the dot product of U and V divided by the length of V. So that's the norm P part, the length of P, times 1 over V times V. Okay, and so this is going to be U dotted with V divided by the length of V squared times V. Okay, again, notice, just pay attention to what's happening here. If I take the dot product of two vectors, that gives me a scalar. So the numerator here is a scalar. If I take the length of a vector and then square it, I get a scalar. I get a scalar with or without squaring it. But the point is that I have a scalar over scalar. So this is just some number. And so then P is going to be that quantity. Okay, so P is going to be that quantity times V. So this is just some stretched vector of V, some dilation of V. So anyways, that's what's called a projection. So P, by the way, is called the projection of U on V. And so if I want to write this, this is U dotted with V divided by the length of V squared. And remember what we said the length of V was, is it's the square root of the dot product of V with itself. And so if I take the length of V squared, I get V dotted with itself. And that's all times the vector V. Okay, so this is called the projection of U on V. That's the idea. Okay, and so if I wanted to compute, just to make this a little bit less abstract, if I wanted to work with a vector U and V. So let's say U is the vector 1, 2, V is the vector 1, 3. What I could do is if I want to compute the projection of U on V, and again, the tails get a little bit tricky to write here, but the projection is just going to be the dot product of U times V. So let's think about what that is. So the dot product of U times V is going to be 1 times 3 plus 2 times 1. So that's going to be 5. And then divided by the length of V squared. So that's V dotted with itself. So 3 times 3 plus 1 times 1. So that happens to be 10. And then times V. So times the vector 3, 1. So that's going to be 1/2 of 3, 1, which is 3/2 times 1/2. And so what this tells us is that if I take the vector 1, 2, so here's our vector U, and then our vector V is the vector 3, 1, and then I take the projection will be this vector, and that looks about right, 3/2, 1/2. Okay, something like that. And again, keep in mind that I can't draw, but that looks roughly the right projection there. Okay, so 3/2, 1/2. And that's the projection. We could also, just since we have these vectors already kind of drawn out, we could also talk about what's the angle between them. So what's the angle between U and V? Well, to do that, what we know is that the cosine of that angle, let's call that angle theta, cosine of theta turns out to be the dot product of U and V. So that's U dotted with V divided by the length of U times the length of V. And so the dot product of U and V we already computed to be 5. The length of U is going to be the square root of 1 times 1 plus 2 times 2. So here we get 1 squared plus 2 squared is 1 plus 4, 5. And then we take the square root. And then the length of V is going to be 3 squared plus 1 squared. So 9 plus 1 or 10. And again, we take the square root. So cosine of theta is going to turn out to be 5 over square root of 5 times square root of 10. So that's square root of 50, or 5 square root of 2. And therefore, cosine of theta is going to be 1 over square root of 2, which means that theta happens to be this nice pi over 4 value. So pi over 4 radians. So it turns out that exactly 45 degrees are between these two vectors. Okay, that's the idea. So that's how you can compute the angle between two vectors u and v. Okay, so that is everything I wanted to say about the projection in general. Okay, and so we've talked so far about the dot product and some nice geometric intuition. We've talked about what it means for vectors to be orthogonal. We've talked about how to find the angle between them, and we've talked about, again, projection vectors and how to find those just with kind of some basic trigonometry. So in the next video, we will extend some of these ideas.